Use the data below from a study of mammograms conducted on women in their 40s to estimate the probability that a randomly selected 40-something woman undergoing a mammogram is found to have cancer or has a false negative mammogram. Okay, so the first thing we want to do when we read this problem is to try to decipher what they're asking us to do. And the nice thing is that it does say we want to estimate the probability. So it's a clear indication that it's a probability problem. But the question is, what type of probability should we use to solve the problem? The next thing we want to pay attention to then is how many items are we selecting, because that will change the type of probability that we are going to use. And it looks like they're only selecting one item, right? A randomly selected 40-something woman. So just one person or one item from this set of data. Okay, so that's good. That means we only have a few choices to consider. Basic probability selects just one item. We also have addition rule of probability, and we'll learn that conditional rule of probability will also involve usually just selecting one item. By the way, of course, we're talking about the most simple examples of these rules, right? Of course, you can, and we'll learn this later, we can blend rules together, right? So you can have addition rule combined with multiplication rule later, or conditional probability combined with multiplication rule of probability. So we can have, example problems where we're using multiple rules to solve a problem. However, we're talking about the most fundamental types of problems here, the simple basic ones that require just one rule used in a pure fashion. So in this case, we're talking about, I think, addition rule of probability, because among the three choices I mentioned that use just one item randomly selected, we have the word or here, and that's a dead giveaway that it's addition rule of probability. So among the three possibilities I mentioned, basic probability, it does not use or as a keyword, right? It would be something like find the probability that a person has cancer. It wouldn't be cancer or something else, right? Conditional probability, instead of using the word or, it would use the phrase given that typically, or assuming that, something like that. So there'd be some assumption stated, and we don't have that here. And also it wouldn't use the word or typically. So for that reason, I think it's addition rule of probability. So let's go ahead and try to solve it now that we think the keywords indicate addition rule of probability. So we're going to write out a probability statement. So probability of, now it says the person does not have cancer or has a false negative result. So I'm going to say C for cancer and put a bar on top to say not cancer, and then I'll write the word or, and then it says false negative. I'll abbreviate that as FN, false negative. Okay, so this is my probability statement beginning. Now, according to the formula, it should be the first thing, probability of that, so not cancer, plus probability of the second thing, false negative, minus the probability of the intersection of the two things. In other words, and I'm going to write this out in a phrase because I want to make sure that we conceptualize this in our mind carefully. So we're going to say that it's women who do not have cancer and have a false negative result. Okay, so let's think about that last piece there. It says probability of women who do not have cancer and have a false negative result. Let's think about that carefully. If you don't have cancer, then if the test says you're negative for cancer, that's not false, that's true, right? In other words, not having cancer means your mammogram should be negative, and that wouldn't be a false negative then, right? A false negative means you actually have cancer, but the test says you don't. So in this case, the mammogram examination can't be a false negative for a woman who does not have cancer. If a woman doesn't have cancer, then a negative result is not false, it's true. So it means it's a correct diagnosis. So in this case, I'm going to say that this is mutually exclusive. And what that means is you can't be a woman who's cancer-free and have a false negative mammogram at the same time, because any negative mammogram would only reflect the reality that you don't have cancer, and so that's not false. So we're going to say that this category is empty, and therefore the probability must be 0. That means you can eliminate it. You can drop it and ignore it. But we can fill out the other two fractions. And the other two fractions are pretty straightforward. We're just going to write it as number of over total, like we're accustomed to doing. So we're going to say number of over total for each of these. Start out with that. And what I want you to do is fill in the pieces that belong in each of these cases. So first thing, what are we selecting? Well, we're selecting a 40-something-year-old woman from the study, right? So they're all 40-something-year-old women, right? So the whole study is for women in their 40s. So we're just going to say total number of women, right? It's number of women. And we can just use that for both because we're only selecting one item. So we're basically just using the same denominator for both fractions. Whenever you're doing addition rule of probability, all three fractions are going to have the same denominator. All right, so let's talk about the numerator now. In this case, for the first fraction, it's going to be number of women who are cancer-free, or another number of women without cancer, right? Without cancer. And for the second fraction, it's the number of false negative results, right? False negatives. Okay, so we can fill that stuff in. So two fractions, and we're going to put our numbers here in the fractions. Okay, so for the denominators, again, as we said, it's 3 million for both. And what about the numerator? The number of women without cancer. So that would be the total for this row, right? Because these are the people or the women who do not have cancer. So this is the group here. So that's going to be a very large number, 2,956,522. That number is so large because, of course, most women walking around do not have breast cancer. So when you test women in general, most of the time you're not going to find women with cancer. All right, let's look at the numerator for the second fraction. It's the number of false negatives. So what's a false negative? It means that a person is in fact stricken with the cancer, but the test says that they don't have it, right? So that means you have to be a part of the cancer row here, but you have to be a part of the cancer row where the test says you're negative for having cancer. So that would be here. So that means that this number here, 10,870, must be the magic number we're looking for. There are 10,870 women who actually had cancer, but were told by the mammogram that they do not have cancer, right? So they went for the screening and the results came back showing they didn't have cancer, but in fact they actually did. Okay, so there's your answer, and you just have to plug those numbers in and do the calculation. You could, if you wanted to, at the end include the -0 for that last fraction that we said was 0, but you don't have to, of course, because subtracting 0 from the answer isn't going to change anything, so I'm just going to leave that off. All right, let's work it out in our calculator and see what we get. So we'll have 2,956,522 divided by 3 million plus, and when you're done, you get 0.989.